Everyone, myself Shiksha Kaushal. The first question which I am going to explain is this. In this question, they talked about hydrogen oxygen fuel cell having 70% efficiency. So, this fuel cell is working under standard conditions at 1 bar and 298 Kelvin, and they have also mentioned its cell reaction. Now, they said that the work derived from this cell on consumption of 10 raised to power minus 3 mole of H2 gas is used to compress 1 mole of monoatomic ideal gas in a thermally insulated container. Okay, and what they are asking is, they are asking the change in temperature of the ideal gas. Okay. Along with that, they have also provided us with the standard reduction potentials for the two cells, which are, this is the first one and this is the second one. Now, for attempting this question, first of all, we have to calculate E naught cell of this given fuel cell reaction. Now, in order to calculate this E naught cell, we will use these two equations to obtain this equation. Now, if you see that if we multiply this whole equation by 2 and then subtract this second equation from the first equation, we will get O2 plus 4H positive aqueous plus 4 electrons minus 4H positive aqueous minus 4 electrons, which gives us 2 molecules of water liquid and minus 2 H2 gas. Now, if we see the overall E naught obtained for this reaction is, E naught for this reaction is 1.23 volt minus, so this is 0. If we multiply it with 2, there will be no difference. So the E naught is 1.23 volt. So this is the overall equation. Now, these will cancel each other and the equation that we'll obtain is O2 gas plus 2H2 gas gives 2 molecules of water liquid having E naught is equals to 1.23 volt. Now, if we can see, this is not exactly equals to this equation. Now, if we divide this equation with 2, the whole equation with 2, this will give us the above equation. So, this will become half O2 gas plus H2 gas is equals to water liquid. But the E naught will not be changed because E naught is independent of these multiplications or divisions that we do to our equation. Now, but one thing which is getting changed here is in this equation we can see that the number of electrons were 4. We can see here that the number of electrons were 4. So the number of electrons are 4 in this equation, but in this equation they will change to 2 electrons. So these were the two terms that we wanted to calculate, that is the number of electrons being transferred, being exchanged, and the value of E naught for this cell. Okay, now let me take this question further. Okay, now they said that the work derived from the cell is used to compress 1 mole of monoatomic ideal gas. Now let us first calculate the work. We know that work is equals to the modulus of change in Gibbs energy, which is further equals to minus NF E naught cell, where N is equals to number of electrons being transferred. F is the Faraday's constant, which is constant whose value is being given, and E naught cell is what we have just calculated, which was 1.23 volt, and number of electrons were 2 electrons. Now a very point to be noted here is that, a very important point, that n is 2 electrons, but we will not substitute n is equals to 2, because the number of electrons were 2 when 1 mole of H2 gas was reacting with the half O2. But in this case, they said that 10 raised to power minus 3 mole of H2 gas is being used. So the number of electrons will become 2 into 10 raised to power minus 3 Faraday's constant into E naught cell. It's not yet completed because this fuel cell is not 100% efficient. This is 70% efficient. So I said that this is a very important point. So we have to multiply it with 70 by 100 because this fuel cell is 70% efficient. Now the value of the work done, as I have calculated, comes out to be 166.173 joules. Okay, so this I have calculated the work. Now they said that this work is used to compress a monoatomic ideal gas in a thermally insulated container. So this is a very important point here, thermally insulated container. So we'll write the value of work, 166.173 joules. Okay. So by thermally insulated container, it means that they are talking about adiabatic process. Adiabatic process. Okay. Now in adiabatic process, we know that Q is equals to 0. That is, the heat transfer is 0. Now if we talk about the thermodynamics first law, which is delta U is equals to Q plus W. So W will be equals to delta U. Also we have derived the equation for work done in case of adiabatic compression, because here they are talking about compression. So the work done in case of adiabatic compression is given by N R delta T over gamma minus 1, where N is the number of moles of the gas, which is 1, R is the gas constant, delta T is the change in temperature, and gamma is Cp over Cv, where Cp is the heat capacity at constant pressure and Cv is the heat capacity at constant volume. So for a monoatomic gas, gamma is 5 by 3. Okay, so this you have to know to solve this question. So W is equals to number of moles into 8.314 delta T over 5 by 3 minus 1. So delta T will comes out to be, after calculating, when we substitute the value of work, so it will comes out to be 13.32 Kelvin. So this was the last thing, this was the question which they have asked. So the main points that we have to focus in this question is that this is a 70% efficient fuel cell. This is thermally insulated container, which means it's a adiabatic compression. Then for monoatomic ideal gas, what is the value of gamma? So in this case, I have solved this question. I hope this answered your question. Thank you.